Good evening once again and welcome to another episode of BJ's Physics Classroom. This episode begins a new series on gravitation. So let's begin. When we talk about gravitational force, it is among the four main forces in the universe. The four main forces in the universe include the weak nuclear force, the strong nuclear force. These two forces are within the nucleus that produce the nuclear binding energy. We have electromagnetic force, that is force as a result of electric charges, and magnetic force, that is what we refer to as electromagnetic force. And the last one is the gravitational force, which is the weakest force in the universe. The gravitational force is the weakest force in the universe. Good. So let me first run you through this basic concept before we start with the Newton's universal law of gravitation. Now, what happens is that the gravitational pull of the Earth is called gravity. Let me explain this. Every object on the Earth's surface or in the Earth's gravitational field gravitates towards the Earth's surface. So what this means is that an object within the Earth's gravitational field is being attracted towards the surface of the Earth. It's being pulled by a certain force we call force of gravity due to the Earth. An object within the Moon's gravitational field is also attracted towards the surface of the Moon. That is also force of gravity due to the Moon. Good. So when we say force of gravity, it is, also a gravitational force, but especially given to the attraction due to the Moon, the attraction due to the Earth. Is that clear? Good. So there is something we call gravitational mass of the body. There is something we call gravitational mass of a body. So when we say gravitational mass of a body, force F is equal to mg. So when we find the mass of a body from the mass of a body which is being acted upon by gravitational force, F over G, this mass is referred to as gravitational mass. Gravitational mass. So the mass of a body under the influence of the gravitational force is what we refer to as gravitational mass. That is one type of mass. Another type of mass that we have is, we call it inertial mass. Inertial mass. Inertial mass. Now, inertial mass is the mass of the body that is under the influence of any external force other than gravitational force. So F is equal to ma. So when we make m the subject, we get F over A. The mass of a body under the influence of any other force other than gravitational force. That mass is what we refer to as inertial mass. So we can talk of these two types of masses under the concept of gravitation. Inertial mass and gravitational mass. Good. So let's deal with the Newton's law of universal gravitation. The Newton's law of universal gravitation states that the force of attraction between any two masses arranged close to each other is directly proportional to the product of the masses and inversely proportional to the square of the distance between the two masses measured from their centers. It means that gravitational force is a central force. Gravitational force is an inverse square force. Gravitational force is an attractive force, and the gravitational force is a field force. These are some of the characteristics of gravitational force. So, mathematically, Newton's gravitational law is represented as this. Let us suppose two masses, M1 and M2, arranged close to each other, separated by a distance r from their centers. The Newton's universal law states that the force between these two masses is proportional to the product of the masses M1 and M2 and inversely proportional to the square of the distance between the two masses, of course measured from their centers. So when we remove the proportionalities and we introduce a constant, F is equal to J M1 M2 all over r squared, where r is the distance between the two masses. The quantity J is called the universal gravitational constant. This quantity J is called the universal gravitational constant, whose value is given by 6.6 times 10 raised to the power negative 11 Newton meter squared per kilogram squared. Newton meter squared per kilogram squared. Newton meter squared per kilogram squared. That is what we make J a subject, exactly. Now the quantity J has the following characteristics. So we say that J, of course, has a value of this one, number 1. Number 2, J is the same throughout the universe. Everywhere you go, the value of J is the same. J is a scalar quantity, and then J is independent on the nature and size of the bodies, as well as the nature and medium between them. So what we're saying is that the value of J is independent on the medium in which the two masses are placed. Unlike electrostatic force, which depends on the medium in which the two charges are placed, this gravitational force is independent on the medium in which the two masses are placed. Good. That is the characteristics of the Newton's universal gravitational constant. So we look at acceleration due to gravity. Now, because of this gravitational force, F, that gravitational force produces an acceleration on every object that is moving vertically in space. That acceleration we call acceleration due to gravity. Now, the acceleration due to gravity is given by the symbol small g. So we want to see the relationship between acceleration due to gravity and the Newton's universal gravitational constant. Relation between small g and capital G. So let us consider the Earth having a mass capital M and an object that is somewhere on the Earth's surface, such that the distance from the object of mass M to the center of the Earth, is given by R. Yes, the gravitational force on this body, F is given by G, capital M, small m, all over R squared. Let me call this equation 1. Then the weight weight of the mass, the weight of this mass, W is equal to mg, the mass of the body times acceleration due to gravity. So what we do is that at this point, the weight of the body is the gravitational force on the body. So the two of them, F and W, can be equated. When we equate the two of them like this, that is going to give us mg is equal to G, capital M, small m, all over R squared. Small m cancels small m. So G is equal to G, capital M over R squared. This is the relation for the acceleration due to gravity of the body. It means that gravitational force produces this acceleration on the body. And you can see that the acceleration due to gravity on the body is independent on the mass of the body that is falling. See, the mass cancel out. So the acceleration due to gravity is independent on the mass of the body. What that means is that irrespective of two masses, two bodies, their masses, one of them can be big, the other one can be small. When they are released from the same height, they will hit the ground at the same time. And this thing was experimented by Galileo Galilei. Alright? What he did was that he picked two different masses, he positioned them on a very tall building, and then he let somebody time for him the time it would take the two objects to hit the ground. And he found out that the two objects hit the ground at the same time. Why? Because they fall with a constant acceleration, which is independent of the masses of the two bodies that are moving. So that acceleration depends on only the mass of the Earth, the universal gravitational constants, and the distance. Since they were positioned at the same height, the distance is the same. So that is constant. Good. So you can be asked to give small differences between capital G and small g. Small g is a vector quantity, capital G is a scalar quantity. Small g varies from place to place, even on the Earth's surface, but capital G is constant everywhere. Small g has unit meter per second squared, capital G has unit Newton meter squared per kilogram squared. So these are some of the differences that exist between small g and capital G. So we say that the gravitational pull on the body, or the gravitational force on the body, is the weight of the body. In other words, the weight of the body is the measure of the gravitational force on the body. And this can be proven, just like what we have done on the board. The weight of the body is the measure of the gravitational force on the body. Look at this. This m is the mass of the body. Capital G, capital M over R squared. Capital G, capital M over R squared. That is the acceleration due to gravity. So the acceleration due to gravity times the mass of the body will give us the gravitational force, which is the weight of the body. So we can define the weight of the body simply by saying the weight of the body is the gravitational pull of the Earth on the body. I hope that is clear. Good. So we look at free fall. You know, acceleration due to gravity is the acceleration, constant acceleration with which an object falls freely on the Earth's surface. Of course, on the Earth's surface, its value is approximately 10 meters per second. On the Moon's surface, its value is approximately 1.67 thereabout meter per second squared. Exactly. These are the values of acceleration due to gravity on the Earth's surface and on the Moon's surface. So any object which is released in space under the influence of the Earth's gravitational force falls with a constant acceleration freely only under the influence of the gravitational force due to the Earth. At this point, we say the object is falling freely, and we call that principle a free fall. Good. We call that principle a free fall. Now, we look at small g. small g. Now, the small g, which is the acceleration due to gravity, vary from place to place on the Earth's surface. And there are two reasons why small g vary from place to place on the Earth's surface. One, the Earth is not a perfect sphere. Well, the Earth is not a perfect sphere. You know, the Earth is geospherical like this. Because the Earth is geospherical, the acceleration due to gravity varies from place to place. Secondly, the Earth is not a perfect sphere because there are mountains and there are valleys. So you don't expect a person inside the valley to have the same distance from that point to the center of the Earth as a person that is on a tall mountain like Mount Nefertiti. You understand that? A person on Mount Nefertiti will have a higher distance from where he is to the center of the Earth. You don't expect acceleration due to gravity at these two places to be the same. Good. The other reason why acceleration due to gravity is not constant in the universe, or it's not constant on the Earth's surface everywhere, is the fact that the Earth is constantly undergoing rotational motion. So the rotational motion of the Earth makes the value of small g, which is acceleration due to gravity, not constant at every place. Good. So if you are asked the factors that affect acceleration due to gravity, we talk about the shape of the Earth, we talk about the rotation of the Earth about its own axis, we talk about altitude. You know, as you move high up into space, the distance between the Earth, the center of the Earth, and where you are increase. As the distance increases, the value of g decrease. And then we have depth. As you go into the Earth's surface too, the value of the acceleration due to gravity decrease. As you go into the Earth's surface, the value of the acceleration due to gravity decrease. So these are the four factors that affect the acceleration due to gravity. Good. At a particular point. Then we talk about another concept that we call gravitational field. Gravitational field. Remember that the Earth or any mass exerts a force around itself. So there is a region around this mass where the force due to the mass is felt. This region is what we call gravitational field. Just like electrostatics, we have electric field, a region around a charge where the electrostatic force due to the charge is felt. Here too we have gravitational field, a region around the mass where the gravitational force due to that mass is felt. That region is what we refer to as gravitational field. Then we speak about another term we call gravitational field intensity. What happens is within the gravitational field, the gravitational force is not the same throughout. So let's assume a mass m has created a field around itself. This mass m has created a field around itself. So within this field, the gravitational force at this point due to this mass is different from the gravitational force at this point within this mass. So the extent of gravitational force at this point is what we refer to as gravitational field intensity. And we define gravitational field intensity as the force per unit mass placed at that point in the gravitational field. Let me take it again. The gravitational field intensity E at a point P in the gravitational field is the force per unit mass placed at that point in the gravitational field. The force per unit mass. The unit for gravitational field intensity is Newton per kilogram. Okay, but you know the value of F is G capital N small n all over R squared. That's the value of the force F. So when we divide it by M to give us divide by M, that will give us the E. This M will cancel this M. So finally, the gravitational field intensity E is given by G capital M over R squared. Funny, right? The gravitational field intensity E is given by G capital M over R squared. Look at this. The unit for gravitational field intensity is given by Newton per kilogram. And Newton is kilogram meter per second squared. So we'll multiply this one by per kilogram will cancel kilogram. Then finally, the unit will become meter per second squared. Which quantity has unit meter per second squared? Acceleration. Under gravitation, we call it acceleration due to gravity. So look at this. The field intensity E is given by J capital M over R squared. The same formula we had for acceleration due to gravity. So we say that the gravitational field intensity at a point in the gravitational field is equal to the acceleration due to gravity at that point. Simple. Good. Then we look at gravitational potential energy. Now, gravitational potential energy is defined as gravitational potential energy and the unit for gravitational potential energy is joules. So gravitational potential energy. The unit, okay, so we say that gravitational potential energy, it is the work done per unit mass. Sorry, we define it as the work done in moving a unit mass from infinity to a point in the gravitational field. Let me explain further. We move a body from infinity. Infinity is any point outside the gravitational field. So we move a certain mass from a point outside the gravitational field into the gravitational field. The work we require to move this mass from infinity to a point in the gravitational field, that work is what we call gravitational potential energy. And the gravitational potential energy at a point is given by G capital M small m over R, then minus. What happens is that the force from which this potential energy was obtained is an attractive force. That is what makes the potential energy becomes negative. Good. Where R is the distance from the center of the body to where we are moving the body to. M is the mass of the body we are moving from infinity to the gravitational field. Capital N is the mass of the body that has created a field. J is the universal gravitational constant. This is the relation for gravitational potential energy. Then we talk about gravitational potential. Gravitational potential. The symbol is V. We define gravitational potential as the force per unit mass in moving that mass from infinity to a point in the gravitational field. V is given by the potential energy per unit mass. We want to move this mass M from infinity to a point in the gravitational field. So the work done per the mass in moving that mass from infinity to this point is what we call gravitational potential. The unit is volts or joule per meter. But because the potential energy is negative here, we put this value here. That will give us V is equal to negative G, capital M, small m, all over R, divided by M. M will cancel M. So V is equal to negative G, capital M, over R. This is the relation for the universe, for the gravitational potential at a point in the gravitational field. So you realize that the gravitational potential at a point in the gravitational field on a mass does not also depend on the mass. Exactly, it does not also depend on the mass. Good. Gravitational potential. Okay, so let me do this. Let me do this small thing. I want to manipulate this equation. Let me write the equation. V is equal to G capital M over R. Let me ignore the negative because the negative is not going to play a role in what I'm going to do. So let me ignore the negative for a while. So we have V is equal to G capital M over R. Let me multiply through this formula by 1 over R. So I'm going to get 1 V over R is equal to G capital M over R all times 1 over R. So this is going to give me V over R is equal to G capital M over R squared. How value is this? Gravitational field intensity. So E is equal to V over R. Therefore, E is equal to, V is equal to ER. You know, it is easy to write the formula like this. V is equal to ER. So another unit for gravitational field intensity is given by volt per meter. Another unit for gravitational field intensity is given by volt per meter. So sometimes you see a question and then we have volt per meter. Sometimes you see a question and then we have Newton per kilogram. The unit is the same. Alright, we're using them to refer to the same quantity. Good. Good. Now let us suppose an object which is placed somewhere on the Earth's surface. Let this be the Earth now. Such that an object is placed somewhere on the Earth's surface on a certain radius. So what happens is that the distance from here to the surface of the Earth, let me call it h. And the distance from the center of the Earth, let me call it capital R, where capital R is the radius of the Earth. All the formulas that I have written down are going to be affected by this. So I decided to put this at the tail end so that it can affect all the formulas that I have written down. So look at this. The gravitational force becomes F is equal to G M1 M2 all over the R squared. But the R squared becomes R plus H all squared like this. So when they give you a question, when you're given a question, and the question requires that the object is not sitting on the Earth's surface or the object is far from the Earth's surface at a height h. Add that height to the radius of the Earth. The value for the radius of the Earth R is approximately 6,400 kilometers. 6,400 kilometers. So when you're dealing with this, convert the 6,400 kilometers into meters before you use it, because the universal gravitational constant is measured in meters. Alright? Good. So, even this formula written here becomes V is equal to G minus G N over R, or capital R plus H. Like this. Then the gravitational field intensity E is given by G capital M over R plus H all squared. Then the acceleration due to gravity is also given by small g is equal to G capital M over R plus H all squared. So in a situation whereby we have an object not on the Earth's surface but situated somewhere at a height h, please make sure that you include that to the radius of because gravitational force is a central force, and the Earth is a big body whose radius is given by 6,400 kilometers. So convert the kilometers, add it to that distance also in meters, and then use it in the formula, and you are good to go. Good. So this brings us to the end of today's episode of the BJ's Physics Classroom. Thank you very much for being part of the show. If you haven't subscribed to my YouTube channel, BJ Online, please do that. When you do that, please turn on the notification button so that anytime a video is posted, you get a notification, then you watch it. Whilst you watch the video, pick your book, study your physics book, any indigenous physics book that you have, study it alongside, and that'll be it for you. Till I see you again with the continuation of the gravitation, which we will deal with satellites, the planets. We will also deal with escape velocities and launching of rockets, and then we'll deal with the Kepler's laws of planetary motion. Till we meet again, thank you very much and stay blessed.